And I'm so glad to welcome you today for another session of AstroTalk project. Today our guest will be Piero D'Incecco, which is a general scientist particularly interested in the surface processes of terrestrial bodies. And before joining the Department of Earth and Planetary Sciences at the Annunzio University and IRSPS in Pescara, Piero he worked at the German Aerospace Center DLR in Germany. And he spent two research periods as visiting scholar in the Planetary Geosciences group at the Brown University in Provence, and he defended his PhD thesis at the Department of Astronomy of the University of Oulu. After obtaining his doctoral degree, he worked as a research scientist for 2 years at the Arctic Planetary Science Institute, APSC, and he is member of the Geologically group GDG of the NASA messenger team. He has been working with remotely sensing data achieved from the surface of Mercury. Piero analyzed the spectral characteristic of fresh unpacked deposit in Mercury using data from European Space Agency Venus Express and NASA Magellan mission. He analyzed the lava flow of the recently active volcanic structures of Venus. His current research activity at the Annunzio University and ERSPS is focused in the exploration of landing site selection of the future robotic and human mission of the Moon. He is also involved in the landing site selection group of the Venera D mission. So today I'm so honored to welcome Piero D'Incecco, which will give us a talk about the geological supervised spectral investigation of the terrestrial bodies, from the Mercury to the Moon. Piero, you can start.
Hello, Mais, and hello, everybody. So basically, Mais already said everything about me and about my past research activity. And this evening I just wanted to show you something what can summarize what was my past research activity and my also about my current research activity. The title of my presentation is Geologically Supervised Spectral Investigation of the Terrestrial Bodies from Mercury to the Moon. I think the title of this presentation summarizes very well, let's say, the work I've been doing so far, because I think that when working with let's say with terrestrial bodies and and with remotely sensed data, it is very important to combine data sets. So it is not enough to just interpret geological data, but we also have to analyze the spectral the spectra basically of the planet. So it's important to combine the geological interpretation with the spectral analysis. And during my career, I have been working basically on 3 terrestrial bodies: Mercury, Venus, and the Moon. These are 3 different, of course, but let's say that I have been trying to develop specific techniques to combine data sets in order to get as much as to get as much as possible information from the crustal properties of each terrestrial body. And of course, in order to do that, we have to consider also what are the let's say the major surface features for each terrestrial body. For example, Mercury is characterized by a lot of impact craters as well as the Moon, while instead Venus it's very different because Venus is a volcanic planet. So when we want to analyze the crustal properties of Venus, we have to focus on volcanic structures. And but let's start from Mercury. So when we analyze Mercury, as I said, we have to focus on UV, have an atmosphere, and it's full of impact craters. As we see in this figure, we have to focus on a specific type of impact craters, which is called complex craters. The complex craters are craters characterized by central resurgence or central uplift, as we see in the figure down to the right, the number 4. It's a little bit the same mechanism when there is a droplet falling into a glass of water. So basically, when we have an impact, there is always when we have an impact where it is large enough, there is always a certain quantity of material which comes up from greater depths, and that's the central uplift. So central uplift represents material coming from greater depths. That's why it is very important to analyze not only the geological features of the surface, but we have to consider also the spectral properties of the surface, because maybe what we are observing can tell us something very important about the subsurface, so about the shallow crust. For Mercury, I have been combining the data sets of two instruments of the MESSENGER spacecraft, NASA MESSENGER spacecraft. On the left side, you can see the MDIS camera. Particularly important was the narrow angle camera, which provided a resolution 30 meters per pixel, which is a pretty high resolution for Mercury. And on the right side, instead, you can see the MASCS instrument, so the near-infrared spectrometer, which allowed us to basically, to analyze the spectral feature of the surface of Mercury. And so as you can see here, this is the study area. I have analyzed two impact craters, two fresh impact craters, complex craters, so craters characterized by a central resurgence. We can see on the left Kuiper crater, and on the right Waters crater, and we can see also the external reference area, which is an area which basically I have selected as a term of reference when analyzing spectra. That we would see that. Here we see the two impact craters. We see on the left Waters crater and on the right Kuiper crater. And these two craters are basically very similar in terms of morphometry and in terms of geological history, and they both sit they both lie on the rim of a pre-existing impact basin, and they are both characterized by a certain quantity of outflowed melt, as we can see. Maybe it's more visible in the case of water impact melt. Impact melt, it's basically melted material. When there is an impact event, of course, we have very high temperatures, and so surface materials melt, basically. But since these two craters lie on the scene, some of the melt outflowed out of the floor of the craters. So these two craters had similar geological conditions, and this is why it was very interesting to analyze them. And they are both characterized by this very important central peak, which exposes material from greater depths, which allows us to see beneath the surface. And for showing basically how I applied this geologically supervised or geologically informed spectral investigation to Kuiper crater, because Kuiper crater is larger and it is clearly visible what I want you to see here. basically I defined you can see on the left side, I defined a number of 5 morphological units. The central peak material in red, and then we see the crater floor terrain inside the crater, and then we see, I also distinguished the internal melt material and the external melt material which outflowed out of the crater. And also, I also defined an area of an annulus of a crater fresh ejecta at 1 radius distance from the rim of the crater. So basically, after defining these units, so these are on the left, you see the geological units or the morphological impact units. On the right side, instead, you see the spectra which are completely contained within each of these morphologically defined units. So this is why I'm in the title, I'm saying geologically supervised spectral investigation or geologically informed spectral investigation, because we give a spectral meaning, a spectral signature to a geologically defined or predefined unit. So for each of these geologically defined units, I have extracted all the available masks, so near-infrared spectra, completely contained within each of these units. So this is also a very tricky thing, because in the program I had to specify that basically the software that I was using should select only the spectra completely contained within each unit. We see that the spectra are characterized by, I don't know if you see my mouse, I'm moving now the arrow of the mouse, but each spectra is characterized by a polygon. I was to the program to choose only the categories of each previously morphologically mapped unit. And we see, here we see the first result, the spectral slope of those geologically supervised spectral units. Unfortunately, we had a problem with the masks instrument, at least at the time of this study, that we couldn't really observe any absorption bands, which is usually that spectral characteristic which is telling us which kind of mineralogy we are observing on the surface. So what kind of minerals we are observing on the surface. We couldn't see that, unfortunately. So what we could see, it was only basically, we could only see if there were like spectral differences and eventually compositional differences between the analyzed surface materials, but we couldn't say what kind of minerals we were observing, unfortunately. So for this reason, we just smoothed the spectra in order to at least analyze in a good way the slope. We can see in red the spectral slope of the central peak of Kuiper crater, and that's quite different from the slope of the external reference area material, what I showed you in the slide before, so which is the term of reference for like indicating the average spectra of the surface of Mercury. So compared to the average spectra of the surface of Mercury, we see that the central peak of Kuiper crater looks pretty different in terms of slope. This implies, and it is even better visible here, we see this plot, we see the absolute average reflectance at 750 nanometers versus the spectral slope, the normalized spectral slope. We see that the reference area, so the external reference area indicated by the blue circle, it's kind of down to the left, let's say, while instead the central peak material, so this material coming from greater depths, Kuiper craters of this crater, characterized by the red square, it's up to the right, so it's pretty far. And this means that we are observing a clear spectral difference are observing, in fact, which means it's the and models. We can really see reconstruct the pre-impact stratigraphy, and so relating, starting from the diameter, from the rim to rim diameter, so from the final diameter of the we could even reconstruct the maximum depth of melting, which corresponds, as we can see here, to the minimum depth of origin of the central peak. So basically, we could understand depth of each layer. So how deep was each layer, with showing a certain spectral heterogeneity. Of course, we can't say, at least at the time of this study, we couldn't say what kind of mineralogy, as I mentioned before, what kind of mineralogy we were observing, but we are sure that we were observing some compositional heterogeneities, and we also could reconstruct at which depth each layer was located. And this is very important. So, I mean, this is what we should do when we analyze terrestrial bodies. We should reconstruct the geologic history, and we should also, of course, we should analyze the crustal properties. Mercury, this is, let's say, a local scale approach. But then I thought, okay, let's be more ambitious. Let's try to apply this this approach on a global scale. Let's try so, as you see, the white circles are the craters I have been selecting. Fresh craters, complex craters, so with this central peak showing this central resurgence, so showing these materials from greater depths. And you see here that it was very complicated to do this kind of intersection, because more than 4 million spectra, so it's really a lot, and it's really demanding also in terms of data processing time, and also in terms of hardware. So I defined basically for each of those 121 fresh impact craters a number of impact units. So we see in red the central peak material, and then we see in orange the crater floor material, and then so on. Crater fresh eject at one radius distance from the rim of each crater, and then other two annuli at 5 and 10 radii distance from the rim of each crater respectively. This was made simultaneously for each of those craters, so it was like a simultaneous procedure. And also the intersection, which in GIS it's called technically spatial join, but it's basically an intersection, as you see also from the symbol here on the left. Basically, yeah, I have said to the software, okay, just tell me what are the spectral observations completely falling within each of those defined units, geologically defined units over all the planet. And then you basically what you see here, this units which are in a way, this is because of the distortion, of course, this is because of the distortion, latitude distortion. So anyway, and here is the result, the global, the result of the global approach. Let's call it like this. You see in red. So the red squares indicate basically the spectral characteristics of the central peak material of each of the 121 impact craters, and you see that the spectral characteristics of those craters of those central peak materials are very sparse, while instead the more we move far from the rim of each crater, the more the spectral characteristics. So the more the more the blue squares basically indicate materials at greater distances from the rim of craters. So basically, we see that they are more clustered because, of course, I mean. Central peak materials, as I said already before, indicate or expose materials from greater depth. So these materials are most likely to be compositionally different. While instead the blue squares, which indicate, let's say, average surface material, they are more like, okay, yeah, they show, of course, the more average spectral appearance. And we can see also that the triangle, the external reference area, in fact, it's located more or less where the cluster of the material at 10 radii distance from the crater is also located. So, okay, this is for Mercury. So on Mercury, we analyzed impact craters. I analyzed with my co-authors, of course, with the researchers who work with me, and impact craters on Mercury. But on Venus, what about Venus? I mean, Venus is different. Venus is like, it's a different thing. Mercury doesn't have an atmosphere. Venus instead has a very dense atmosphere. Is a very different planet, and when we want to analyze the crustal properties of Venus, for us is not we can't rely on impact craters. I mean, we have impact craters on Venus, but impact craters are not the main surface features, geological features, when we want to analyze the geological history of this planet. When we want to analyze instead the geological history of Venus, we have to analyze the volcanic structures, so volcanoes, because Venus is a planet volcanically, which has been, in terms of geological time, it has been recently active. In terms of geological time, so I'm talking about thousands of years. But it may be according to recent studies, it may be still active at present. So this is why applying this, what I like to call the dataset fusion techniques, was also very important on Venus, but in a different way compared to Mercury, in the sense that, okay, here is the study area, first of all. A recent study has shown that there is especially one volcano on Venus, which is named Ibn Mons, and it is 200 kilometers across, or 120 miles, let's say. It's located in a young, already in what can be also defined as a young area of Venus, and the volcano itself has been identified from, you can see here, from the Venus Express spacecraft and from the VIRTIS instrument, which is a near-infrared spectrometer. It has been identified as a very, very young portion of the surface of the planet. Why this? You see the red spot. This red spot, I don't know if you can see the arrow of my mouse, but anyway, over this volcano, what you can see with the dot, basically surrounded by the lines. So you can see this red spot, and this red spot indicates high emissivity anomalies. Why the emissivity anomalies at 1 micron wavelength are so important on Venus? Because on Venus we have very high, very fast chemical weathering. Which means that surface material on Venus we have like very fast chemical reactions between the surface and the atmosphere. So at the boundary between the surface and the atmosphere, we have a lot of chemical reactions which act very fast, and the oxidation of the surface material on Venus is very fast as well. So when we observe 1 micron emissivity anomalies, basically we are observing what is technically called unweathered material, which means that we are observing fresh surface deposits. Well, if we observe potentially fresh surface deposits on the top volcano, of course this can mean that we are maybe observing like fresh lava flows, and maybe we are observing volcanic activity still active at the moment, who knows. So this is why it was very important to apply those kind of techniques also on Venus when we want to reconstruct the crustal properties of the planet, because of course through the volcanoes we can also get an idea of what is beneath the surface, so what is inside the planet. And so to do that, okay, so here we have, I combined basically two data sets. On the right side, you see the Magellan radar data set, and on the left side, you see the Magellan radar data set. And on the right side, instead, you see the VIRTIS data set, so of infrared spectra. Why this? Because there was this red spot, but from this red spot of spectra, so infrared spectra, it wasn't possible to really understand the source and location of those anomalies. So even if we have active lava flows, we didn't know if those lava flows were coming like from the top of the volcano, or maybe from from lateral vents of the volcano. So in this, the radar data set of the Magellan SAR instrument came in help, because we have much higher resolution when it comes to the geological mapping of the surface of Venus. So we see here that it was possible to map. I mapped actually 5 lava flows, one top composite unit in red on the top of the volcano, and then 4 flank lava flows using the radar images, which are pretty useful when we want to analyze the surface of Venus. And then using I performed an emissivity modeling. We performed all together, I mean, with those stakeholders, we performed an emissivity modeling, assigning a value of an hypothetic value of emissivity to each of the mapped units, and then we saw basically what was the we got what is called an RMS error. So what is the difference between the model and the observation of the spacecraft? So when we got so basically the scenario which reproduced the smallest error compared to the observation of the spacecraft was the scenario where we gave the high emissivity values to the flank units, which means that basically the scenario what we reproduced, which approached the most the observations of the spacecraft, was the scenario where the flank units are the responsible for these high emissivity anomalies, which means that according to our model, it's most likely, let's say, that the lateral flows are the source, the actual source of those anomalies. And so this means that if volcanic activity recently took place on this volcano, it may be more possible that it took place from lateral lava flows and not from the top. But okay, I mean, this is just an example of what it is possible to do using these techniques. And the one important point is that using, and here is again, let's go back to geology, using cross-cutting relationships, we could even reconstruct, basically, we also again made a tentative reconstruction of the post-eruption stratigraphy on the top and then the eastern flank of these volcano islands. And so, we made a kind of, how to say, a blind check, because on one side, we analyzed the spectral properties of these lava flows, and on the other side, we analyzed the geological, we made this geological analysis, and without considering the results of the spectral properties. And then we found out that even from the geological analysis, it turned out that the flank lava flows are actually look to be more recent. So this confirms, in a way, the results of the spectral analysis, which tells us that the flank lava flows may be more recent. So, I mean, this is a kind of this is the kind of analysis what can be done, for example, on a planet like Venus. And so, what's going on now on Venus? I mean, there are a couple of missions, like also for Mercury. Before I didn't mention, but also for Mercury, we have now the Bepi Colombo, which is a very important mission, because I mean, it would really improve everything what we have seen with the messenger mission. Is going to be improved, and we can look more. We can look much deeper into the crustal properties of the planet, thanks to the instruments, to the higher resolution instruments mounted on the Bepi Colombo spacecraft. And also for Venus, the same thing. I mean, for Venus, we really need a new mission, because the last remarkable mission, I mean, we had the Venus Express. Then before that, we had the Venera missions, and we had, of course, the NASA Magellan mission. But we need a new mission now, because we need really to explore better this planet. We need to know more about the crustal properties of the planet. We need to know more about, for example, if really volcanism is still active, and how old is the surface of Venus. And so we have a lot of science key questions but we need to answer. And so in this, I mean, there is also the Venus Exploration Analysis Group, the VEXA group, which is making great effort to coordinate basically the science work of all the researchers. But as I said at the beginning, my current work is now focusing on my current research activity is now focusing on the moon, which is the next frontier of the space exploration, as I wrote also on this title, because at least this is what I really strongly believe. Because why? First of all, we have been on the moon, so we have the technology to reach the moon. We have been there, so we know how to go there. And the moon, it's close. It's also closer than other terrestrial bodies. And also, the moon might store, as I wrote here, considerable quantities of water ice and important minerals, for example, titanium, or but even more common minerals like iron. I mean, we don't know, but we have to explore the moon because there may be really important minerals what we may use also for our world economy. And especially because if we want to build a human colony on the moon, we need really, first of all, we need water, and then we need minerals to exploit, of course. So we need to look for specific locations on the moon. And the moon is also useful because we can use it, let's say, as a base camp to prepare the astronauts for having longer trips to, for example, to Mars, I may say, which is also one of the other targets. And so, as I was mentioning, if we look at the moon, what are we looking at? We are looking for, first of all, for water ice, because if we want to build a human colony, we have to look for water ice, and to do that, but we also have to take care that we need solar energy. So it's complicated because water ice is where, like it's always, we have more possibilities to find water ice in the so-called permanently shadowed regions. So in those regions which are never touched from the sunlight. But if we want to build a human colony, we also need solar light, of course, solar illumination. So it's very tricky. If we want to build a human colony in the future, we need to look for areas on the moon which are like kind of in the limit, the boundary between those so-called permanently shadowed regions and illuminated areas, so that we can get solar energy, and we can also get areas, we can get also reservoirs of water ice that can be, of course, used to maintain the human colony. And then we should also take a look at the potentially available minerals, what we can exploit not only for the colony but also, as I said, for the world economy. So, and even in this case, it will be very important to combine data sets, because it's not only enough to consider to look at our science target when we are analyzing terrestrial bodies. It's not only enough to look at the geological side, but we also need, of course, to analyze the spectra or maybe even the temperature layer. So, I mean, there are a lot of different data sets what we have to consider here. For example, I have I'm showing just a selection of some missions, which can be very useful when performing this kind of geologically supervised spectral investigations on the moon. We have the Lunar Reconnaissance Orbiter, which mounts a camera, it mounts also a neutron spectrometer, and then we have the Chandrayaan, India's first lunar probe. I mean, the Chandrayaan mission, which is a very important mission because it provided infrared data. And then we have the future mission. So I mean, we have a lot of things going on the moon as well, and we need to be able to combine data sets in order to, of course, to answer the science questions, what are really important for the future of the space exploration. Sorry. Okay. So I mean, this is it. Hello.
Yeah, we are here, Piero. So
yeah,
you finish it?
Yes. This is yes.
Okay, thanks a lot, Piero, for the interesting presentation. It was really cool, like to have a big tour between Mars, Mercury, and the Moon. No, in fact, Mercury, Moon, and Venus. So we are welcoming question right now. If someone have question.
Lisa?
Yes.
I have question.
Yeah, go ahead.
Thank you, Mr. Piero, for this talk. It was very interesting. So my question about the Mercury spectrometer, the Mercury atmospheric and surface composition spectrometer. Which kind of spectrometer? Is it mass spectrometer, atomic absorption spectrometer, or for example, atomic emission?
No, it's a near infrared.
What the paper crater?
It's a near infrared spectrometer.
Infrared.
Mm-hmm.
Okay, and my second question about the mineral or the chemical composition. You said that you analyze the mineral, which are inorganic composition. What about the organic composition? Are you not interested by the analysis of organic?
Where, first of all, what planet are we talking about?
Mercury.
No, I mean, the thing is that for Mercury, I wouldn't say that that's the main target, but the point is that it wasn't possible to analyze any specific mineralogy with the masks instrument. I mean, we couldn't be really sure about the mineralogy of the surface with the masks instrument, at least at the time of this study. So, but anyway, we were talking about inorganic mineralogy. Of course, I mean, for the future, who knows, but I would say that for the moment, maybe for Mercury, but this is my personal opinion, I would say that that's, I mean, it's more important just to understand the mineralogy.
Okay.
Yeah.
Thank you so much. Thank you.
Oh, you're welcome.
Okay, Piero, I have a question concerning your slide where they are the global scale approach. So, how do you know it's like clustered there? What kind of interpretation that lets you say, okay, here we do have a cluster?
Yes. Can you see here? This is the plot we are talking about now.
Mm-hmm, mm-hmm.
Yes. So. Sorry.
So how do you know that we do have a cluster here? So what kind of analysis or interpretation that led you say, okay, in that data I do have cluster?
I mean, we were analyzing. I should show you more data because I mean this plot is really let's say it's a summary. So there are many more data what I should show you in order to explain better what is in this plot. But basically, we're also analyzing the standard deviation. So we were analyzing a lot of other parameters in order to define this as a cluster. Let's say that the standard deviation of the central peak materials it's larger than the standard deviation of the external reference material or of material like at 10 radian distance from the rim of the craters. But this is very like synthetic as an explanation. But yeah, there are a lot of more data what I could show you. Maybe we could also discuss later this. We could also have a follow-up on this because I mean it's pretty complicated. So I was just showing here the one plot in order to show you to show all of you the let's say the technique. But behind there is a lot of other data what should be, of course, shown.
Okay.
I had a question regarding this plot as well.
Oh, hi, Sam, it's you?
Yes, hey.
Yeah. Hi.
Why would we expect the surface material to be more homogeneous in this distribution than why would we expect the surface material to be closer clustered or have a lower variance than the stuff in the subterranean bits?
Well, that's a very good question, Sam. Thanks a lot, actually. And this is something what I forgot to mention when talking about Mercury, because I kind of mentioned it when talking about Venus, but I didn't mention it when talking about Mercury, which is space weathering. So when we observe surface material on atmosphere-less, I'm not sure if it's like this, but I mean on planetary bodies without an atmosphere, we get a process called space weathering, which is basically a chemical modification of the surface material due to the solar radiation, for example, or micrometeorite impact, and which basically tends to uniform to make the spectral characteristics of the surface material more homogeneous with the time. So this is why, after a certain amount of time, all the surface material, due to this process called space weathering, gets spectrally more homogeneous. When we have a fresh impact crater, for fresh I mean geologically recent impact crater, we have, of course, that the central peak, the central resurgence, not only exposes material from greater depths, but exposes material which is potentially very fresh and unweathered. So it didn't go through this process of space weathering. So it's unweathered, let's say. And this is also a second very important thing what we have to consider when analyzing the central peaks of impact craters on planetary bodies like Mercury, but also on the Moon, because I mean also the Moon is full of impact craters and basins. So this can be very useful. So this is why the spectral characteristics of like average surface material tend to be more homogeneous than fresh central peaks.
So it is sort of an analogous argument to the Venus the argument for recent Venus volcanic activity, right?
Exactly.
You're seeing stuff that has been exposed to less environmental degradation or so, and so you've got fresh material, for lack of a better word. Okay, that makes sense. Thank you.
Yeah.
Okay, Piero, what scientific target behind the study of Venus? Because We know Venus is like, yeah, it's interesting from the volcanic point of view, but what kind of scientific target that we can carry out through the study of the geology of the surface?
Well, in a way, the volcanism on Venus is it's pretty connected to the geologic history of Venus, so it's very important. I mean, volcanism it's part of the geologic study of Venus. So through volcanism, we can really understand. Let's make an example. Analyzing the volatile content of the lava flows on Venus. I have an idea also of the rheology of the mantle. And there is a key question on Venus, which basically there is a big debate whether Venus is still going through the so-called equilibrium, catastrophic resurfacing, or maybe it's evolving through a stage of more equilibrium resurfacing. So the thing is that it is supposed that Venus had gone through a huge volcanic resurfacing, so a huge eruption, global eruption, about, let's say, 300 million years ago, according to the model. And after that, so we the rheology of the mantle, because I mean, depending on the rheology of the mantle, we can still, for example, understand if really Venus is still going through these events of catastrophic resurfacing every, I don't know, every several hundred million years, or maybe it's evolving toward a situation of more equilibrium resurfacing, like, yeah, I mean, I don't want to say like we see on Earth, because I mean, Venus is very different from the volcanism on Venus is different from that of the Earth. So, but there are really important questions, science questions, which analyzing the volcanism on Venus can be answered, and of course we need new missions to answer these questions.
Okay, Fresh, go ahead.
Hi everyone, thank you for this lecture. So my question for dear conference about the method of spectral analysis. Is it's the same thing for the exoplanets, or it's different?
Well, I'm not an expert. I have to tell you honestly, I'm not an expert of exoplanets. So, I mean, let's say that these methodologies can be potentially applied, of course, to many different fields, even outside planetary sciences. I may even say some examples of how to apply these techniques out of planetary sciences. But for what concerns, yeah, I mean, it would be better to ask, but there's something wrong, so I prefer just not even answer. I just can tell you that I personally think we kind of maybe in a modified version, but the datasets fusion techniques can be, of course, applied also to many different fields.
Okay, thank you.
Hey Pierre, I got another question.
Yeah.
All right. So when you're scouting out good landing sites on the moon, you were talking about the importance of solar energy. Are there other plans for human activity or whatnot that involve nuclear power instead, so that they don't have this further restriction on suitable places?
Well, what do you mean by nuclear power programs? I mean,
sorry. So the idea is that
I'm not sure if I understood.
Well, presumably you want solar radiation for the sake of powering or for the sake of energy, right? That's what I assume you meant. Yeah. Well, I mean, if you had a nuclear reactor, that would not be a restraint, would it?
I think it would be definitely better to have like solar panels than having nuclear nuclear powers. This is my personal opinion. I mean, so when selecting a landing site, I would say that it's anyway dependent of the source of energy, what you want to use, if it's nuclear or solar. I mean, it's anyway better to have solar energy on available, let's say, and it's very important, because it makes also a colony more sustainable. So,
okay, Pierre, I do have two questions. So, since Mercury has more crater and impact marks than any other planet, so could be Mercury, let's say, the lastest stage of our moon?
The thing is that studies from performed using the data set of the Messenger mission show that Mercury and the Moon are pretty different, and so I'm not sure we can say really that that Mercury is the last stage of like the geological formation of the Moon. I would say that they are different. Okay, so we can't really make a comparison in this sense.
Okay, and the second question is like the selection of possible landing site in the moon. So what criteria should we use to say, okay, this area could be a possible landing site? So do you use like geological maps or the mineralogy of the area or the structures, or what kind of criteria?
So we use actually everything what is available. So everything is important when selecting a landing site. It's a very, very tricky procedure, and so it's a very delicate decision that of selecting a landing site, not only for the Moon but also for Venus or for whatever terrestrial body. So for sure, recent studies have shown that on the Moon, a particularly interesting area is the southern pole, because on the southern pole have been identified really have been identified the indicators of what could be the occurrence of water ice. So this is a very important thing, because of course if we are looking for a landing site on the Moon, we need, as I said before, we need first of all a reservoir of water ice. So the southern pole of the Moon would be already like an interesting area to look at. And then we have, as I mentioned before, also we have to be looking for places at the boundary between the permanently shadow regions and the illuminated areas. There are a couple of craters, couple of impact basins in the southern pole of the Moon, which may be already like interesting places for a landing site. For example, there is the Cabeus. There is the Cabeus crater, which is very interesting in this sense. But there are a couple of craters which may be selected for further studies. First of all, of course, we need to look for water ice, and of course, we also need to look for minerals which may sustain a potential human colony. But to do that, to identify the minerals, we need first of all to analyze the spectra. So we need also to analyze the spectral data sets. So the selection of a landing site involves the coordination of a lot of efforts, and it requires to look at the problem from different point of views, and so not only from the geological point of view, but also from the point of view of the spectral analysis, as well as for Mercury or for Venus. I mean, but especially for the Moon, because the Moon is the next frontier. I mean, we are getting there now.
Does someone have a question? Okay, Piero, we do have another question from Raouf. He say, thanks, I'm geologist. So what is the relationship between a fracture trend and eruption surfaces?
If I understand well the question, a fracture trend is more like a tectonic feature, while what was the second, sorry? May you repeat me the question?
Yeah, he say, what is the relationship between fracture trends and eruption surfaces?
Yeah, and yes, the eruption surface, I mean, it's related to volcanism, so it's different. It's like more or less the same difference what we have between tectonism and volcanism. I hope I understood well the question. So, but yeah. Oh, sorry, this noise is.
Okay, and here in the chat we do have a question from Jarmo. He say, if you could study anything, what will be the most interesting topic to study right now?
Well, this is a very difficult question. I mean, it's a great question and very difficult at the same time, because I mean, space exploration, it's beautiful. I mean, it's what I love personally. So for me to choose between one terrestrial body and another one, it's very difficult. And, let's say that there are also implications, important implications in terms of where we are going as a human species. So the world economy, we have to look not only at the scientific side, but sometimes we have to think also about how can we be useful as scientists for the world economy, for example, and for the development of us as a human species. So in this sense, I'd say that I couldn't choose actually, but I like the direction of exploring the Moon for the moment, because it's probably the terrestrial body what we are really able to explore in the short term. I think the Moon, it's there. I mean, it's really that terrestrial body that we can really explore in the short term. So for this reason, because it's closer and we have the technology to reach it, I would say the Moon. But we shouldn't forget that the exploration of the solar system. The exploration of the space exploration in general, it's extremely important. So it is impossible to make a real choice.
Okay, if someone have a question for Piero. Okay, then I do have like personal question. Why you are focused in the study of crater in Mercury? For example, in Mercury, we can like one of the interesting features is like the faults are also rich, and there are like many structures. So why your study is focused in the crater specifically, let's say so?
Since the idea was that of combining data sets, impact craters on Mercury as well as on the Moon offer an incredible opportunity to combine data sets, because I mean, we can analyze the central peaks, which are a pretty unique feature, what can give us the opportunity to study the subsurface of the planet. So in this sense, I saw the analysis of the impact craters as a pretty unique opportunity to apply those so-called datasets fusion techniques. It's nothing about, of course, a personal preference. I mean, I just thought that to apply those geologically informed spectral investigation, probably the impact craters were the best feature, and especially the central peaks. Yeah.
So, any other questions? Okay, so since we don't have any more questions, I'd like to thank Piero again. Thanks, Piero, for the nice presentation and for your amazing work about Mercury, Moon, and Venus. Thanks again, and we hope that we meet again for another talk.
Oh, thank you very much, Maisa, and thank you everybody for listening and for being here this evening with us.
Thank you everyone for your participation, and thank you. Goodbye. Bye-bye.
Bye-bye.
Thank you.
Bye.
Gosh.